The M1A1 Bazooka was supposed to be America's tank-killing miracle weapon, yet by late 1943, frontline reports painted a devastating picture. Rockets were bouncing off German armor like tennis balls off concrete walls. What seemed like a fundamental design failure would trigger one of World War II's most ingenious engineering solutions, transforming how shaped charges could penetrate moving targets at seemingly impossible angles. In the muddy fields of Italy, American infantry crouched behind crumbling stone walls, watching their anti-tank rockets ricochet harmlessly off panzer hulls. The acrid smell of cordite mixed with diesel fumes as German tanks continued their advance, seemingly invulnerable to America's premier infantry anti-tank weapon. The metallic clang of deflected rockets echoed across battlefields where desperate soldiers discovered their primary tank-killing tool was failing them when they needed it most. This investigation reveals how a seemingly simple modification to the M1A1 Bazooka's ammunition would revolutionize shaped charge effectiveness against moving armor, challenging everything military engineers thought they knew about penetrating angled targets. The solution lay not in more explosive power, but in counterintuitive physics that would redefine anti-tank warfare for generations. Staff Sergeant Mike Kowalski pressed his eye against the M1A1's crude optical sight, tracking a Panzer IV as it rumbled across the Italian countryside at 15 miles per hour. The 2.36-inch rocket launcher felt solid in his hands, its 34-pound weight distributed between him and his loader, Private Danny Chen. Intelligence briefings had promised this weapon could penetrate 4 inches of armor plate at 300 yards, enough to stop any German tank in production. The mathematical reality seemed straightforward. The M6 rocket's shaped charge warhead contained 1.59 pounds of Composition B explosive, designed to create a superheated copper jet capable of burning through hardened steel. At impact velocities of 265 feet per second, the high explosive anti-tank heat round should have been devastating against enemy armor. American Ordnance engineers had calculated penetration capabilities based on perpendicular impacts against stationary test plates, but battlefield conditions rarely matched laboratory specifications. As Kowalski squeezed the trigger, sending the rocket streaking toward its target with a distinctive whoosh, he watched in horror as the projectile struck the Panzer's sloped frontal armor and deflected skyward like a skipping stone. The pointed nose cone of the M6 rocket had encountered the tank's hull at approximately 30 degrees from perpendicular, causing the entire warhead to ricochet without detonating its shaped charge. Chen frantically loaded another rocket while Kowalski cursed the weapon that was supposed to give infantry a fighting chance against German armor. Across the Mediterranean theater, similar scenes played out daily as American soldiers discovered their primary anti-tank weapon's critical vulnerability. The M1A1 Bazooka's effectiveness dropped catastrophically when engaging moving targets or tanks positioned on slopes, precisely the conditions most common in actual combat. The pointed nose design of the M6 rocket had seemed logical during development at Aberdeen Proving Ground in Maryland. Ordnance engineers reasoned that a sharp, aerodynamic nose would improve accuracy and ensure proper fuse function upon impact. The rocket's 4 stabilizing fins, spanning 2.75 inches, provided excellent flight stability during the weapon's maximum effective range of 400 yards. Initial testing against perpendicular armor plates had validated the design's penetration capabilities. However, these laboratory conditions failed to account for the geometric realities of tank combat. German tank designers had learned harsh lessons during the early war years, incorporating sloped armor that could deflect incoming projectiles while maximizing protection without adding excessive weight. The Panzer IV's frontal armor, though only 3.15 inches thick, was angled at 30 degrees from vertical, effectively increasing its protective value while creating deflection surfaces. When the M6 rocket's pointed nose struck angled armor, basic physics took over. The initial contact point concentrated impact forces on the nose cone's tip, but instead of penetrating, the rocket's momentum carried it along the armor's surface. The shaped charge's copper liner never achieved proper standoff distance, and the explosive never detonated in the precise configuration required for armor penetration. American infantry found themselves armed with an anti-tank weapon that worked perfectly in testing, but failed consistently in combat. Reports from the Fifth Army in Italy documented dozens of instances where M1A1 teams had achieved direct hits on German tanks without causing significant damage. Tank crews reported hearing metallic impacts followed by the sight of American rockets tumbling through the air, their warheads unexploded. The psychological effect on American infantry was devastating, as soldiers lost confidence in their primary means of stopping enemy armor advances. Lieutenant Colonel Leslie Skinner, the M1A1's original developer, received urgent field reports at his Aberdeen Proving Ground office in October 1943. The manila folders contained detailed after-action reports from Italy, each documenting the same disturbing pattern: rocket deflection at oblique impact angles. Skinner had spent years perfecting the bazooka's basic design, drawing inspiration from Dr. Robert Goddard's rocket research and adapting it for infantry use. The reports painted a clear picture of systemic failure. In one documented engagement near Salerno, a single M1A1 team had fired 7 rockets at a Panzer III, achieving 6 direct hits without penetrating the tank's armor. The German crew had eventually withdrawn, not from damage but from ammunition depletion. Similar accounts arrived from Tunisia, where American forces had first encountered the limitations of their anti-tank rockets against experienced German tank crews who understood how to position their vehicles for maximum deflection. Skinner's engineering team faced a fundamental challenge: how to ensure shaped charge detonation against angled targets without compromising the rocket's aerodynamic properties or increasing its weight beyond infantry portability limits. The M6 rocket already pushed the boundaries of what a 2-man team could effectively operate, with each round weighing 3.4 pounds and measuring 18 inches in length. Any modification would need to maintain these constraints while solving the deflection problem. The solution required abandoning conventional wisdom about projectile design. Instead of refining the pointed nose, Skinner's team began experimenting with blunt nose configurations that seemed to contradict basic aerodynamic principles. Wind tunnel testing at Aberdeen revealed that a properly designed blunt nose could actually improve the rocket's stability while solving the deflection problem through entirely different impact mechanics. The breakthrough came through studying the physics of shaped charge detonation, rather than focusing solely on penetration mechanics. Dr. Monroe's research on the Monroe effect had established that shaped charges required precise standoff distances and detonation timing to achieve maximum penetration. The pointed nose design, while aerodynamically sound, created unpredictable contact conditions that prevented optimal shaped charge function. Engineers discovered that a blunt nose design would ensure more consistent impact characteristics against angled armor. Instead of sliding along the armor surface, a blunt nose would create immediate distributed contact that triggered the rocket's impact fuse more reliably. The shaped charge would detonate at proper standoff distance, allowing the copper liner to form its penetrating jet before the target's angle could cause deflection. Testing began with modified M6 rockets featuring progressively blunter nose designs. Each configuration underwent ballistic testing to measure accuracy degradation, followed by penetration tests against angled armor plates. The optimal design emerged as a hemispherical nose that maintained acceptable accuracy while dramatically improving performance against oblique targets. This configuration would become the foundation for the M6A3 rocket. The blunt nose design also addressed another critical issue: fuse sensitivity. The original pointed nose often failed to trigger the impact fuse when striking at shallow angles, as insufficient impact force was transmitted through the nose cone's narrow contact point. The blunt nose created a larger impact surface that ensured reliable fuse function, even when striking heavily angled targets, guaranteeing shaped charge detonation under combat conditions. Private First Class Tommy Rodriguez crouched in a bombed-out farmhouse near Anzio, watching German tanks maneuver through the morning mist of January 1944. His M1A1 Bazooka team had received the new M6A3 rockets just 3 days earlier, along with strict instructions to test them against any available targets. The ammunition looked different from the familiar M6 rounds, with a distinctly blunt nose that seemed almost crude compared to the sleek, pointed design they had grown accustomed to. Rodriguez's loader, Corporal James Washington, examined the new rocket's unusual nose configuration. The hemispherical front end seemed to defy everything they had learned about projectile design. Yet their sergeant had assured them these rounds would solve the deflection problems that had plagued their previous engagements. The rocket still weighed 3.4 pounds and measured 18 inches in length, but its appearance suggested entirely different impact characteristics. A Panzer IV emerged from behind a stone wall, its commander scanning for American positions through his cupola periscope. The tank's hull was angled at approximately 25 degrees as it navigated the uneven terrain, presenting exactly the type of oblique target that had caused so many previous failures. Rodriguez steadied his aim, compensating for the tank's movement, while his loader prepared a second round. The M6A3 rocket struck the Panzer's frontal armor with a distinctive, deeper impact sound, compared to the metallic clang of deflected M6 rounds. Instead of ricocheting, the blunt nose maintained contact with the armor surface long enough for the impact fuse to function properly. The shaped charge detonated at optimal standoff distance, sending a superheated copper jet through the tank's armor and into the fighting compartment. Field reports from Anzio documented a remarkable transformation in American anti-tank capabilities. The M6A3 achieved a 340% increase in successful penetrations against angled targets compared to the original M6 rocket. The blunt nose design had solved the deflection problem, while actually improving the shaped charge's effectiveness through more consistent detonation conditions. Production of the M6A3 began at Picatinny Arsenal in New Jersey, with manufacturing capacity rapidly scaling to meet frontline demand. The rocket's copper liner was refined to optimize jet formation, while the Composition B explosive charge was precisely calibrated for the new nose design. Quality control procedures ensured each rocket met strict tolerances for nose geometry, as even minor variations could affect impact characteristics against angled armor. The transformation in American infantry morale was immediate and profound. Soldiers who had lost confidence in their anti-tank weapons suddenly found themselves capable of stopping German armor advances with reliable effectiveness. M1A1 teams began actively seeking engagement opportunities, knowing their weapons could now function as intended even under adverse impact conditions. German tank crews noticed the change within weeks of the M6A3's introduction. Previous tactics of angling their hulls for maximum deflection became less effective as American rockets began penetrating armor that had previously been immune to bazooka attack. Tank commanders were forced to modify their engagement procedures, maintaining greater distances from American infantry positions and avoiding terrain that might expose them to close-range rocket fire. The engineering triumph of the M6A3 prompted immediate development of improved launcher variants to maximize the new rocket's potential. The M9 Bazooka incorporated structural reinforcements to handle the M6A3's improved performance characteristics, while adding an optical sight for enhanced accuracy against moving targets. The launcher's aluminum construction was strengthened at critical stress points to prevent damage from repeated firing. Manufacturing data revealed the scope of the improvement program's impact on American war production. Picatinny Arsenal produced over 400,000 M6A3 rockets between January and June 1944, while simultaneously phasing out production of the problematic M6 variant. The retooling process required modifying nose cone forming equipment and implementing new quality control procedures to ensure consistent blunt nose geometry. Field testing expanded beyond the Mediterranean theater as M6A3 rockets reached American forces in the Pacific. Against Japanese armor, which typically featured thinner protection but often operated in heavily angled positions due to terrain constraints, the new rockets proved even more effective than in European combat. Marine Corps units reported near-universal success rates against Japanese tanks when using the improved ammunition. The M6A3's development also influenced broader American ordnance philosophy. The triumph of the blunt nose design challenged conventional assumptions about projectile aerodynamics, leading to similar modifications in other shaped charge weapons. Artillery shells, aircraft rockets, and even naval ordnance began incorporating lessons learned from the bazooka's transformation. Technical analysis of recovered M6A3 warheads from successful penetrations revealed the precise mechanisms behind the blunt nose's effectiveness. High-speed photography captured the shaped charge detonation sequence, showing how the hemispherical nose ensured optimal standoff distance, even when striking armor at angles up to 45 degrees from perpendicular. The copper liner formed its penetrating jet with remarkable consistency, regardless of impact angle. Metallurgical examination of penetrated armor plates demonstrated the M6A3's superior performance characteristics. The copper jet maintained coherence and velocity through angled armor that would have deflected pointed nose rockets, creating clean penetration holes with minimal spalling. German armor samples showed evidence of complete perforation, even when struck at previously impossible angles. The blunt nose design also improved the rocket's terminal ballistics in unexpected ways. Wind tunnel testing revealed that the hemispherical nose actually reduced drag during the final phase of flight, as the rocket's velocity decreased below critical aerodynamic thresholds. This characteristic improved accuracy at longer ranges, while maintaining the impact energy necessary for armor penetration. Studies compiled by Army Ordnance documented the M6A3's revolutionary impact on infantry anti-tank capabilities. Success rates against moving targets increased from 23% with the M6 rocket to 78% with the M6A3, while effectiveness against stationary angled targets improved from 31% to 89%. These improvements transformed the M1A1 from a marginally effective weapon into a reliable tank-killing system. Sergeant First Class Anthony Ricci led his M1A1 team through the rubble-strewn streets of Cassino in March 1944, carrying the confidence that came with proven weapons. His team had successfully engaged 4 German tanks using M6A3 rockets, achieving penetrations that would have been impossible with the earlier pointed nose ammunition. The psychological transformation was as significant as the technical improvement, as American infantry no longer felt helpless against enemy armor. Ricci's combat experience illustrated the broader tactical implications of the M6A3's effectiveness. Infantry units could now engage tanks from positions that offered concealment rather than optimal firing angles, as the blunt nose rockets could penetrate armor even when striking at severe angles. This flexibility allowed American forces to maintain defensive positions in urban terrain, while still threatening German armor advances. The rockets' improved reliability also enabled new tactical doctrines. M1A1 teams began coordinating with artillery observers to engage tanks that had been damaged but not destroyed by indirect fire. The combination of artillery suppression followed by close-range rocket attack proved devastatingly effective against German armored formations attempting to withdraw from bombardment areas. Training procedures evolved to emphasize the M6A3's capabilities against angled targets. Infantry schools began teaching engagement techniques that maximize the rocket's effectiveness while minimizing exposure to enemy return fire. Soldiers learned to exploit terrain features that would position enemy tanks at disadvantageous angles, turning the battlefield geometry to their advantage. German intelligence efforts to understand the American improvement led to detailed examination of captured M6A3 rockets at German ordnance facilities. Engineers struggled to comprehend how a seemingly crude blunt nose could outperform their expectations of American anti-tank technology. The analysis revealed sophisticated understanding of shaped charge physics that German engineers had not anticipated from American ordnance development. German countermeasures focused on tactical modifications rather than armor improvements, as the weight penalties of thicker armor would have compromised tank mobility. Tank crews received training in rapid movement techniques designed to minimize exposure time to American rocket teams, while commanders emphasized the importance of maintaining maximum possible distances from infantry positions. The psychological burden on German tank crews became evident through prisoner interrogations and captured documents. Tank commanders reported increased stress levels when operating in areas known to contain American infantry, as the improved bazooka effectiveness had eliminated many previously safe engagement positions. The knowledge that angled positioning no longer provided reliable protection forced German armor tactics to become more conservative. Intelligence reports indicated that German ordnance engineers attempted to develop similar blunt nose improvements for their own shaped charge weapons. However, the Panzerfaust and Panzerschreck programs had already committed to pointed nose designs, and retooling production would have required resources that Germany could not spare in 1944's increasingly desperate military situation. Production statistics revealed the massive scale of America's commitment to the M6A3 program. By D-Day in June 1944, American forces had accumulated over 600,000 improved rockets, ensuring that every M1A1 team in the European theater of operations would have access to the enhanced ammunition. Manufacturing quality control maintained defect rates below 0.3%, ensuring reliable performance under combat conditions. The economic impact of the M6A3 program demonstrated American industrial capacity's ability to rapidly implement improvements. Retooling costs at Picatinny Arsenal totaled $2.3 million, while the improved combat effectiveness prevented an estimated $47 million in equipment losses and casualty-related expenses, while improved combat effectiveness accelerated campaign timelines and reduced overall war costs. The program demonstrated how relatively small investments in weapons improvement could yield disproportionate strategic benefits. Logistics networks adapted to support the new ammunition's distribution requirements. The M6A3's identical dimensions to the original M6 rocket simplified transportation and storage, while distinctive nose markings prevented accidental mixing of ammunition types. Supply officers received specific instructions to prioritize M6A3 distribution to frontline units, while gradually withdrawing remaining M6 stocks. Training ammunition production paralleled combat round manufacturing to ensure adequate preparation for replacement personnel. Practice rockets with inert warheads but identical ballistic characteristics allowed soldiers to master the M6A3's handling without expending combat ammunition. This training program proved crucial as American forces prepared for the Normandy invasion. The Normandy landings in June 1944 provided the ultimate test of the M6A3's effectiveness against German armor in the bocage terrain of northwestern France. The hedgerow country's confined spaces and limited visibility created ideal conditions for close-range anti-tank engagements, where the improved rocket's ability to penetrate angled armor proved decisive in countless small unit actions. Staff Sergeant Robert Chen's M1A1 team exemplified the weapon's tactical impact during the breakout from the Normandy beachhead. Operating in terrain that channeled German tanks into predictable routes, Chen's team achieved 7 confirmed kills using M6A3 rockets, including 3 Panzer IVs that had positioned themselves at angles that would have deflected earlier ammunition. The psychological effect on German defenders was profound, as previously safe positions became vulnerable to American infantry attack. Battle reports from the bocage fighting documented the M6A3's effectiveness in urban and semi-urban environments. The rocket's ability to penetrate angled armor allowed American infantry to engage tanks from building positions that offered concealment, but not optimal firing angles. This capability proved crucial in village fighting, where geometric constraints often prevented perpendicular shots at enemy armor. The cumulative effect of improved anti-tank capabilities began influencing German tactical doctrine at the operational level. Tank commanders received orders to avoid close contact with American infantry whenever possible, leading to more conservative employment of armored reserves. This tactical shift reduced German armor's effectiveness in counterattack operations, contributing to the eventual collapse of German defensive positions in Normandy. Technical analysis of the M6A3's copper liner revealed sophisticated metallurgical engineering that maximized the shaped charge's effectiveness. The liner's thickness varied from 0.040 inches at the apex to 0.065 inches at the base, creating optimal conditions for jet formation regardless of impact angle. This precision manufacturing required new quality control procedures that ensured consistent performance across hundreds of thousands of production rounds. Ballistic testing demonstrated the M6A3's superior performance against various armor types encountered in European combat. Against homogeneous armor plate, the rocket could penetrate 4.7 inches at perpendicular impact and 3.2 inches at 30-degree angles. Face-hardened armor, common on German tank fronts, showed penetration values of 4.1 inches perpendicular and 2.8 inches at 30 degrees. These capabilities exceeded the protection levels of most German tanks in service during 1944. The shaped charge's jet velocity measurements revealed the physics behind the M6A3's effectiveness. High-speed photography captured jet formation at 26,000 feet per second, with coherence maintained through angled armor penetration. The blunt nose design ensured optimal standoff distance of 2.1 times the warhead diameter, regardless of impact angle variations caused by target movement or terrain irregularities. Comparative testing against captured German anti-tank weapons showed the M6A3's superior performance against angled targets. The Panzerfaust's pointed nose design suffered from similar deflection problems that had plagued the original M6 rocket, while the Panzerschreck's larger warhead could not compensate for poor impact angle performance. American ordnance engineers had achieved a significant technological advantage through innovative design rather than increased explosive power. The M6A3's influence on post-war American ordnance development philosophy established blunt nose design as standard practice for shaped charge weapons. The Korean War would see this technology refined further in the 3.5-inch Super Bazooka, which incorporated lessons learned from the M6A3's development. The principle of optimizing impact characteristics rather than simply increasing explosive power became fundamental to American anti-tank weapon design. International military observers studied the M6A3's development process, recognizing the importance of field feedback in weapons improvement programs. The rapid transition from problem identification to solution implementation demonstrated American industrial capacity's responsiveness to combat requirements. This model influenced post-war NATO standardization efforts and shaped charge weapon development across Allied nations. The engineering principles established by the M6A3 program extended beyond anti-tank weapons into broader ordnance applications. Artillery shells, aircraft rockets, and even naval ordnance incorporated similar nose design modifications to improve effectiveness against angled targets. The shaped charge physics understanding gained through the Bazooka program contributed to developments in oil well perforation, demolition charges, and industrial cutting applications. Veterans' accounts from the European theater consistently emphasized the psychological transformation that accompanied reliable anti-tank weapons. The knowledge that their primary anti-tank weapon could function effectively against angled targets transformed American infantry from defensive-minded troops into aggressive tank hunters. This confidence factor proved as important as the technical improvements in determining battlefield outcomes. Analysis compiled by Army ground forces documented the M6A3's strategic impact on American infantry capabilities. Tank kill ratios improved from 1.2 kills per 10 rockets fired with the M6 to 4.7 kills per 10 rockets with the M6A3. Representing a nearly 400% improvement in ammunition efficiency. This enhancement reduced logistical requirements while increasing tactical effectiveness across all theaters of operation. The rocket's improved performance enabled new tactical doctrines that emphasized infantry anti-tank capabilities in combined arms operations. Tank destroyer units could focus on long-range engagements, while infantry handled close-range threats, creating layered anti-tank defenses that maximize the effectiveness of available resources. This tactical evolution contributed significantly to American success in the final year of European combat. Economic analysis revealed the M6A3 program's exceptional return on investment. The $2.3 million development and retooling cost prevented an estimated $47 million in equipment losses and casualty-related expenses, while improved combat effectiveness accelerated campaign timelines and reduced overall war costs. The program demonstrated how relatively small investments in weapons improvement could yield disproportionate strategic benefits. The M6A3's development timeline, from problem identification to full production deployment in less than 6 months, established new standards for American ordnance responsiveness. This rapid development cycle became a model for future weapons improvement programs, emphasizing the importance of maintaining close communication between combat units and development facilities. The achievement validated American industrial capacity's ability to solve complex technical problems under wartime pressure. Field reports from the final months of European combat documented the M6A3's continued effectiveness against Germany's most advanced armor. Even the formidable Tiger I, with its 4-inch frontal armor, proved vulnerable to the improved rocket when struck at optimal angles. American infantry teams achieved confirmed penetrations against Tiger tanks in at least 12 documented engagements, demonstrating the M6A3's capability against the heaviest German armor in service. The rocket's performance against the newer Panther tank revealed both capabilities and limitations of the shaped charge design. While the M6A3 could penetrate the Panther's side armor reliably, the tank's 3.9-inch frontal armor, at 55 degrees, presented challenges even for the improved ammunition. These engagements provided valuable data for post-war anti-tank weapon development, highlighting the need for larger warheads against increasingly heavy armor. Intelligence reports indicated that German tank crews had developed specific countermeasures against the improved American rockets. Tank commanders emphasized rapid movement and smokescreen deployment to minimize exposure time to infantry anti-tank teams. However, these defensive measures reduced German armor's offensive capabilities, contributing to the increasingly passive employment of armored reserves during the final campaigns. The M6A3's psychological influence extended beyond immediate tactical effects to influence German strategic planning. Intelligence assessments suggested that improved American anti-tank capabilities contributed to German decisions to concentrate armor in defensive positions rather than risk mobile operations. This tactical shift played a significant role in the collapse of German defensive flexibility during the final Allied offensives. Production records from Picatinny Arsenal revealed the massive scale of M6A3 manufacturing during the war's final year. Peak production reached 85,000 rockets per month, with quality control maintaining defect rates below 0.2%, despite the intense manufacturing pace. The production line employed over 3,200 workers operating in 3 shifts, demonstrating American industrial capacity's ability to maintain precision manufacturing under wartime conditions. The manufacturing process incorporated numerous innovations developed specifically for the M6A3 program. Automated nose-forming equipment ensured consistent hemispherical geometry, while improved copper liner production techniques enhanced shaped charge performance. These manufacturing advances reduced production costs by 23% compared to the original M6 rocket, while delivering superior combat effectiveness. Quality assurance procedures included ballistic testing of sample rockets from each production batch, ensuring consistent performance across the entire manufacturing run. Test firing at Aberdeen Proving Ground validated accuracy, penetration capability, and reliability under various environmental conditions. This comprehensive testing program maintained combat effectiveness while identifying potential production issues before they could affect frontline ammunition supplies. The economic ripple effects of M6A3 production extended throughout American industry, as subcontractors supplied specialized components and raw materials. Copper liner production required coordination with mining operations, while explosive manufacturing demanded careful scheduling to maintain safety standards. The program demonstrated American industry's ability to rapidly scale specialized production, while maintaining quality and safety requirements. The M6A3's influence extended far beyond World War II, establishing design principles that shaped anti-tank weapon development for decades. The Korean War's 3.5-inch Super Bazooka incorporated refined versions of the blunt nose design, while NATO standardization efforts spread these principles throughout Allied military forces. The shaped charge physics understanding gained through the M6A3 program contributed to numerous post-war military and civilian applications. Veterans' reunions consistently featured discussions of the M6A3's impact on infantry confidence and tactical effectiveness. Soldiers who had experienced both the original M6's limitations and the M6A3's reliability emphasized the psychological transformation that accompanied the technical improvement. The knowledge that their anti-tank weapon would function reliably against angled targets fundamentally changed how American infantry approached armored threats. Technical documentation from the M6A3 program became required reading at post-war ordnance schools, establishing the rocket's development as a case study in responsive weapons improvement. The rapid transition from problem identification to solution implementation demonstrated the importance of maintaining close communication between combat units and development facilities. This model influenced American military procurement philosophy throughout the Cold War era. The engineering principles established by the M6A3's development contributed to broader advances in shaped charge technology. Oil well perforation, demolition applications, and industrial cutting tools all benefited from the improved understanding of shaped charge physics gained through the Bazooka program. The military investment in anti-tank weapon improvement yielded unexpected dividends across multiple civilian industries. Modern analysis of the M6A3's development reveals the sophisticated engineering that transformed a failing weapon into a combat-effective system. Computer modeling of the shaped charge detonation process validates the original engineer's intuitive understanding of the physics involved, while demonstrating the precision required to achieve consistent performance against angled targets. The blunt nose design represented a counterintuitive solution that challenged conventional projectile design assumptions. The M6A3's contribution to World War II's outcome, while difficult to quantify precisely, significantly enhanced American infantry's tactical effectiveness during the war's final year. Improved anti-tank capabilities enabled more aggressive infantry tactics, reduced casualties from failed engagements, and enhanced overall combat effectiveness. The rocket's development demonstrated how relatively small technical improvements could yield disproportionate strategic benefits. Historical assessment of the M6A3 program highlights the importance of responsive weapons development in modern warfare. The ability to identify problems, develop solutions, and implement improvements within months rather than years proved crucial to maintaining technological superiority. This rapid development cycle became a model for future American military procurement, emphasizing the need for flexible, responsive development processes. The transformation of the M1A1 Bazooka from a marginally effective weapon to a reliable tank-killing system through the M6A3's development represents one of World War II's most remarkable weapons improvement programs. The blunt nose design's ability to penetrate angled armor at previously impossible angles revolutionized infantry anti-tank capabilities, proving that innovative engineering could overcome seemingly insurmountable technical challenges and fundamentally alter the balance of power between infantry and armor on the modern battlefield.